Such a pleasure working with you this summer. Thanks for taking the time to work on our project. It has been fantastic to see you grow as a researcher and coder, especially with such a difficult project. We wish you the best of luck with your future endeavors, especially grad school, and we hope to see more AGN, starbirds, and merging galaxies in your future. And so Dion is going to tell you about his work on ultraluminous infrared galaxies and JWST that he's worked on. So. Oh. Good. So what's going on?
I'm going to see.
No, that's not what you see.
Oh, sorry. I got too many that thing.
Okay.
I just need the password, sorry.
Yeah. That was on me.
So hi everyone. I'm Dion. I went to school at Towson, and I did my summer scholar project on ultraluminous and like the infrared galaxies in JWST. Oh, sorry. So, audio. Okay. You're good. So the purpose of my project was to see how H2 affects the ISM, the interstellar medium, and how star formation is impacted in the merger I saw. In my presentation, I'll be going over some background information, my purpose, my results, and my conclusions. Some background information on my project I use in integral field spectroscopy cube of a 47 by 47 pixel field. And the wavelength it ranged from 11.5 to 14 microns. I first took a single pixel of the 47 by 47. I used the 20 by 30, and this is just a single point along the line. And this allowed me to see an individual addition line that I could fit. And also I use like the rest of my graphs are all of the 47 by 47 pixels. So it basically shows the entire galaxy. And how come this how come this patterns is that purging galaxies and AGN can launch outflows or streams of gas and dust that push outwards. These outflows can remove materials that could have formed stars. So like they can either slow down or like just completely shut off star formation. This process is called AGN feedback, where energy from the supermassive black hole affects the gas around it. I will also be going over three main things in the purger: the gas brightness, the gas motion, and the gas turbulence of the H2. The brightness is how strong the emission line is. The motion is the wavelength. So it's basically like if it's a redshifted or blue shifted, and the turbulence is how broad the line is. And like these measurements will tell us how the gas or the H2 in this case is behaving in the merger, and it lets us know the potential of the star formation inside of the merger and the locations where stars would form. So this is like my first my first like 20 by 30, which is just a singular pixel of the overall 47 by 47. This graph shows the spectrum from the one spot, as I said, the 20 by 30. The x-axis is the wavelength, the y-axis is the flux, or basically just saying of how bright the like how bright the pixel is at each wavelength. That we decided to shorten it from the 11.5 to 14 to 12.9 to 13.3 is just because the H2 was being shown more prominently of like around 13.008 of microns. So we wanted just that to be shown. So we shortened it to the 12.9 to 13.3. We use the masking function, which is like basically it took away all of like of the wavelengths from 12.8 and below and 13.3 and over that. So the thing you see right now is just that condensed wavelength of that cube, but just for this singular spatule. The blue is basically the original spectrum of the line that is within that 12.9 to 13.3 microns. As you can see right here, this little space right here is where the H2 is being shown. It basically indicates where the H2 is the strongest at. The orange line right here is basically the continuum, which is just a smooth the background height from the warm cusp. And the green line is just the subtracted of this continuum, and this is basically it shows us the pure emission line after that, and then the red line is basically the Gaussian curve, which basically shows the amplitude, the center, and the width. The peak is 13.008, and the width is about 0.046, which is basically small. So it's basically saying there's little to no turbulence, there's little outflow, and it's not really active. And the amplitude is basically shows where the line is. Sorry, it's like it shows the strongest. Like that it shows the emissions when it's the strongest. So here is the 47 by 47 pixel of the whole galaxy. It goes in like but this chart it basically shows off the brightness of the H2. So as you can see along the edges, the H2 is the most brightest, and it goes on a scale from 0.008. And this scale was determined by me and my mentors. Again, the X and the Y axis is just the 47 by the 47. So H2 is the brightest along the edges, as you can see, and in the center is between like a 003 to 006, which is saying that it's H2 in there, but it's not like as bright as it is on the edges, and there are very few aspects of it where there's barely anything in it at all. So it's parts right here or parts right here where there's no H2 at all, which makes it hard for stars to form, because stars need molecular clouds that is primarily made of H2 to form stars. So in areas like here, there wouldn't be like any star formation, but along the edges and even in the centers, stars still have a good sum to form. This is where the gas is moving. So like again, like the x-axis is basically, and like the y-axis is essentially just, you know, the 47 by 47 pixel, which shows the entire galaxy. And the scale was determined by me and my mentor to show like the blue and the red shift, which basically is saying the H2 and the outer skirts is going out, like, so like it's moving away. So like the H2 is primarily going around the edges, again as shown, and this means the H2 is going in, like the blue shifted, and this right here is the center. So it's faint, like a faint red shift, but it's still, I guess, a red shift in a way. The blue shows a negative velocity, and it's just like the gas is moving up away, towards the center, and the red is a positive, and it means it's going away. Yeah. And this is where like the gas is the most active. And this is the scale again, was determined by me and my mentors to show the turbulence. There's a lot of turbulence along the edges. And this is kind of, I would say, it's like, because like the H2 H2 that's not settled, it can't really form the molecular I would say the clouds that is needed to form stars. So like in areas where it is like the 800, the 700, the 600, even like the 5, it will be more harder to form stars in this area because of the high turbulence of H2. So in even areas in the center, where the AGN is, or it can be, is still highly, that is really not going to be like too much star formation because it's so turbulent. Now areas where like here, kind of like in, I would say on the ISM, where like is low turbulence, stars can be active here or form here, but it really depends again on the amount of H2 in these areas. So in conclusion, this this purger, I don't think that it will produce any stars because of the high turbulence, say caused from the AGN and the H2 gas being pushed out of the galaxy. But if it did produce, it would be along the center of it, and like the last slide I showed, it would be like in that space that's not as turbulent and that has a good amount of H2 in it. And for my future part, we were supposed to do a similar thing for like the velocity, like the amplitudes and the turbulence with say with Dion, to like see how it would affect it, but we didn't have the opportunity to like see how that would form stars. But yeah, that's my
Can you explain a little bit more why turbulent might limit star formation?
Yeah, so I'm not sure I can go back on here actually. Oh, I can go back. So H2 is kind of like the primary thing that is used to formulate stars, because it needs it to be settled for it to form a molecular cloud. So if it's turbulent, it can't ever settle. So if it don't ever settle, then stars can't be formed out of that.
How did you choose the size of your pixel map? You said it was 47 by 47 pixels.
Yeah, that was just what the size it it was. They didn't like, I guess, explain to me how come it was like that. It was just that they were just like, here is it, you work with it.
Good job, thank you.
Very nice talk, Dion. Given how sort of obvious the merging galaxies are in the center of the field, what do you feel like you can say about like the relationship between the edges of this field where you seem to have like really active, or at least spectrally active stuff going on, and then a whole bunch of like empty space, and then a bunch of stuff right in the core where the bits are merging?
I think honestly, it has a lot to do with the red and the blue shifted. It's just because that the gas itself is on the outskirts as is, and if the gas from like the center is constantly being pushed like out and out and out and out, this would, I guess, cause this or like the spots over here to be I guess like excreted out even more, to where like this is now space where it's just like it's H2 in this space, but it's still not like, I'm not sure how like I've had to explain it. But like it's still here, but it's just a lot of space that's just like it's in a state of being both red and blue shift, if that makes any sense. I'm not sure like if I described it right, but yeah.
Great, thank you very much.
Okay. All right, so next up we have Diepanh. So some words from Brian, her mentor. It's been such a great time working together this summer. IceCube is a big and complicated experiment, but she has fearlessly tackled all of these topics: statistical tools, the detector's design and operation, and more. Diepanh has had insightful comments and has always had new questions about how things work and how to move forward with the science. Her tenacity and growth has been a joy to witness. Today, we're going to hear about search for neutrinos from fast X-ray transients.
So thank you guys so much for being here. It means a lot to me. So I'm Diepanh, and this summer I'm working with Brian on the search for neutrino from fast X-ray transients with IceCube. So first we'll introduce what neutrinos are. So neutrinos are a low mass leptons in the standard model. This picture is from Fermilab, and it contains so these are neutrons, and they contains of three flavors, which are electron, muon, and tau. Neutrinos are produced of hadronic interaction. So this is an indication of that if we see neutrinos in a source, it's likely to be of hadronic origin. In astronomy, we also have a neutrino as a messenger, and which I can explain more. In our like humans' effort to understand the universe, we have had like cosmic rays or other like photons like X-rays, gamma rays to just look into the universe. A problem with cosmic ray is that they have charge, so they are banned by the magnetic fields as they travel. So like even though we are like on Earth able to see where see a cosmic ray, we can't tell like where it comes from. But the problem with photons like gamma rays, X-rays, that they are photons, so they do interact with photons or dust in the universe. So they might not come to us, and like we can't see them. But we have an alternative solution, which is neutrinos. A thing about neutrino is that they are neutral, so have no charge, and they are weakly interacting. So if you are on Earth and you can see neutrinos coming from somewhere, it's way easier to pinpoint what the source is. And the reason why we are interested in these sources is that they might be extreme phenomena like exploding stars or merging black holes. Yeah, moving on. So we now see neutrino as a source detection. So we hope that they will be the perfect chase into the way further into the universe. But a problem with them is that they are very, very hard to detect because they don't have charge and they don't really interact a lot. But when they do interact and we are able to catch them, when they do interact, they will emit these optical Cherenkov lights that you can see on the right. Like it actually have that visible blue light like that. And so we are building a neutrino detector called IceCube to detect this emission. So we'll capture this light to study neutrinos. So we'll talk about IceCube. IceCube is built. IceCube is a neutrino detector built under the ice of Antarctica. So they are this very huge, and you can see how huge it is by comparing it to the Eiffel Tower right here. So like these are like the strings of IceCube, and on these strings, like in total we have 5,160. We call these like DOMs or like digital optical modules. So these are these are photomultiplier tubes that can not only detect the light that we discussed, but only can like filter or like send the data back for processing and analyzing. Yeah, and we also have the IceCube lab up here. So in the IceCube, in IceCube, we see like these two main kinds of events, or the shapes. So these are called tracks, and over there is cascades. So I'll try if I can play a video of these to show. Well, I can't access the video. These are on YouTube. I don't know why like these don't show the play buttons. But as you can see, tracks look like this. Cascades look like that. So tracks are a better indicator of where sources come from, or we can say it has better angular resolution. Because like if you try to fit a line here, you can see like way easier where the source might come from. However, a problem with them is that because like they travel a really long way, so they might interact outside of the detector and just travel inside. So we can't really capture all the light of it, or like all the energy. So we can't. So the method to reconstruct energy from tracks is harder. While compared to cascades, it had like these two are like kind of like complement each other. So cascades, once they interact, it's mostly captured by IceCube, but so it's better to reconstruct its energy, but the angular resolution isn't as good. So so now we'll talk about the type of data in the data set that we received from IceCube. So as you can see, so we classify they have as like two different categories. So one is source, which is astrophysical neutrinos. These are astrophysical neutrinos, and then the other is background, which are atmospheric neutrinos or atmospheric muon created by cosmic rays. And in within the scope of our research, we are only interested to search for astrophysical neutrinos. So these will be the background data. Astrophysical neutrinos, or we also refer to them as source. So where are we gonna search for them? We'll be searching for them. First of all, we'll talk about how we can like maybe see if our data set is just contain entirely of background data, or it's better explained by having both data, a background and source in it. So this now becomes a statistical or a hypothesis testing question, where the null hypothesis is the data set is just background, versus the alternative hypothesis is the data set contains of both background and signal. And there's this is called the test statistics, a measurement of which kind of like situation we are in, like whether it's just background or background plus signal. And the way we study or we construct this number is by studying the spatial, energy, and time distribution. So let's talk about the time for a minute. So time. We'll be searching for neutrinos in fast X-ray transients, which happens in a very short time, and they are also very interesting because they are very bright and it's easier for us to pinpoint where the source is. Let's go back to the time distribution. So we want to search for neutrinos that happen within a time window of the fast X-ray transient. Yeah, just keep in mind the phrase time window. Fast X-ray transients are detected by the Einstein probe, which is recently deployed, and they look for X-ray flares. There are also the data we took from are published on the GCN circulars. Also, this is a past detection of fast X-ray transients that make us believe that fast X-ray transients are hadronic, which indicate that like they likely to produce neutrinos, and this is a past evidence, past detection of it. So one of our goals this summer is to put together a catalog of fast X-ray transients to be able to work with. So we have run like Python codes to parse data from the GCN circulars, and this is a plot of where the locations of the fast X-ray transients are, and these are the ones that we have. Not only that, we also calculate the TS distribution, the test statistic distribution. To be able to be able to see, like, to tell that whether the data set contains of signal data as well, we'll first want to have like a picture of like what it will look like, what the TS values will look like when it's just background versus when there's signal in it. So we run trials to see what are like the likelihood that there's like signal data in our data set. So on the left is background trials when the number of signal is 0, versus on the right is like when we force number of signal events. When we force signal events to be in our data set. So as you can see, these two distributions are very different. On this side, like you can see, like we run 1 million trials for this one, and nearly 1 million trials give the TS value of 0, and the 3 sigma level is just like when like 99.9% of the data also fall on the left, like also are 0, which is really nice because like when there's no signal, it's anyways, on the right, so this is when we force two signal events in our data set, and you guys can see that like this gives a very different distribution. On average, we can expect the TS values given to us to be over 45, and this indicates that with such a very low number of this indicates that we can detect a source with very low number of signal events, because this is just 2 and number of signals just equal to, but the TS value is just like very different. So yeah. So I guess these are the work that I've done this summer. Moving towards, so yeah, we do have a conclusion that FXTs are promising. Why? Mostly because it has a very small time window, which reduce the noise. Moving forward, we also want to calculate the flux level correspond to different number of signals. We also want to test different time windows. Right now we're doing 1,000 seconds. And we also want to look at different stacking and reading skips. And also we want to add more or modify the data within our catalogs to have better FXT data to work with. I want to thank everyone that has helped me throughout this summer. I want to thank my mentor, Brian. I want to thank the GRAD-MAP lead and my fellow GRAD-MAP students. And I want to thank the UMD Particle Astrophysics group, especially Bennett, for helping me so much with the codes and the stats. Yeah, thank you guys for your time. Music.
It's the one of those files.
I run them overnight, so I wasn't paying much attention. But so for the file, the background files is like 1 million. I think it's like maybe can be up to 10 hours. I think the one on the right, is just like it's 100,000. So maybe like 5-ish hours. Yeah.
So how do you separate the source from the astronomical neutrino?
The source from the astronomy.
Or like the astronomical neutrino from atmospherical, sorry, my bad,
Yeah.
Atmospherical neutrino.
So we are you talking about like when we try to run trials or
Like, is there any property of neutrino that is different in astrophysical neutrino and atmospherical neutrino that helps us separate? Okay, this is an atmospheric neutrino and that is an astrophysical neutrino.
Good question. So we separate them based on our understanding of the spatial energy and time distribution. Actually, like mathematically speaking, we separate them based on something called the likelihood function, where I can show so the one like on the second equation. So this is the probability density of its being signal versus being background. So the probability of it being signal, we take into account both the spatial, the time, and the energy of the event happening.
You mentioned that you combine different information. Do you know which one is more dominant when distinguishing these two kind of sources?
So for that, I don't look too much. Are you talking about like between like spatial?
Yeah, yes.
For that, I haven't looked too much into the equation, but I'm pretty sure that I'll look more into it and I can actually send you the formula.
Right. Right, next up we have Ashok, who is Ashok Paudel, who is from Texas State University. And before Ashok starts, I'm going to read the statement that their mentor Robert Stein wrote about working. Ashok was not a typical Astro GRAD-MAP student, having a background in engineering rather than in astrophysics. So I was a little nervous at the beginning about how things might go. Luckily, I was worrying over nothing. Ashok is so enthusiastic about astrophysics research, even more than I am, and has really thrown himself into the task. He's done great work consistently and managed to complete the project in the very short duration of the program. He's also been such a pleasure to work with. I always enjoy our meetings because of his curiosity and drive. It's been great to see him master things over the course of the program, and I'm sure he'll excel wherever he goes. And this is going to be on buttons.
Checking. Okay, let's get started. Hi, I'm Ashok, and I'm here to present my summer research program titled Photometric Classification for Transient Detection with Rubin under the mentorship of Robert. So let's get it started. This is my presentation outline. We'll talk about TD, light curves, how to separate TDs from imposters, how Rubin is revealing more TDs, how do we narrow our candidate from the sources, candidate light curve fit, future step for our thing, acknowledgement, and summary. Okay, so at the center of most of the galaxies lies supermassive black holes. For most of the time, they are inactive. But when an unlucky star gets too close to that supermassive black hole, we experience something interesting. So the black hole's gravity pull much more strongly on the near side of the star than on the farther side. This differential gravitational force is called tidal force, which causes the star to get stretched out, and the star is disrupted, hence causing tidal disruption event. This creates a bright flash of light that you, me, and astronomers can see with their telescope. Why this is important to us? Because they provide us with an unique opportunity to study inactive black holes. Okay, this is what the typical light curve of a TD look like. So on the top is the light curve. It shows the characteristic rise and fade of a TDE. Rise is relatively shorter in span, spanning in days and months. The fall is relatively longer, spanning month and years. The apparent magnitude is how bright it does look to us, and the absolute magnitude is how bright it actually is. It has a constant or like slow color evolution. On the bottom is the temperature evolution of that TDE. As we can see, it also has a constant or a slow temperature evolution. It has relatively high temperature and less uncertainty. Okay, it's good that we have TD to understand black holes, but there is a story. There are imposters that we need to separate from, as TD isn't the only coolest thing that happens in our universe. The first imposter is AGN, which stands for active galactic nuclei, which is a continuously fading black hole that also lies at the center of the galaxies. The second imposter is a supernova, which is a big star explosion. It also mimics somewhat like TD in terms of rise and fade, but it has a rapid change in temperature and color. And of course, the visible star that we see twinkling at night. So we need to come up with something that helps us separate TD from these imposters. How do we do that? So the problem is we can't look at every source and identify it manually because of the overwhelming number of TDs that we can detect from Rubin. Let's talk a little bit about Rubin. Let's talk first about GTF, which is an old generation sky survey. They are expected to detect almost like 30 TDs per year, relatively low number. But Rubin is the next generation sky survey, a multi-billion-dollar project that is expected to detect more than 3,000 TDs per year. Rubin reaches sources almost 10 times fainter than the GTF or the current sky survey that we have. So it detects a volume of the universe thousands times bigger. The problem is spectroscopy, which is like analyzing light in details for each of the sources, too expensive for us. So instead, we use photometric classification. Less is more for us. Just using brightness and color help us study millions of sources that we detect from Rubin, allowing us to study some of the darkest centers of the universe. So what we did in our summer research project is that we built a multi-step filter. First, we have around like 11,000 sources from the Rubin that were detected until June 15, 2026. Then what we did is that we look at all the AGN that we have. Remember, I told you that AGN and TD happens at the center of the galaxies. So we look at something called host offset. What is an offset? It's an angular separation between the center of the galaxy and the host. So we wanted to look something that is nuclear or at the center or near the center of the galaxy. So as you can see from the graph, 80% of our AGN have a offset of 0.25 arcsec. So that helps us estimate that if a source have an offset 0.25 arcsec or less than that, then we say that, okay, they are located at the center of the galaxies. So that is there for you. Then we remove all the known AGN and star using different catalog data that we have. After that, we did the main thing. it is GP thermal fit. How do we do that? So what we do in this is that we treat each source as a black body. And we fit the Gaussian process, fit black body to that multi-band color data that we have to each of the sources. The output is the observed peak temperature and a fit quality from 0 to 1. After we did that, we did the redshift correction. Because for the same data, if some source is located near to us, it will have different absolute brightness and rest frame temperature. Or if it is farther, then we will have a different rest frame temperature and the absolute brightness. So we need to take that into account. Then what we did is that we get the final TD candidate by looking at a fit score greater than 0.7 so that we can get a good curve fit. And we also look at the temperature more than 10,000 Kelvin. Why do we do that? Because TD are relatively hotter. So after we did that, we got some results, We got some results from almost like 11,000 candidates that we have at the beginning of our study. We narrowed it down to 17 promising candidates. It was cool looking at them. So host offset was our biggest filter. As I say, it was able to cut almost 2/3 of our sources. Then we removed the AGN, then we removed the star, and then we did the GP thermal fit, where 619 were the only promising candidate that has enough data so that we can fit that GP thermal fit. So we try to apply these filters that will help us reduce as many sources as we can. So, okay. So after we do the GP fit, this is what the curve fit look like. So a typical candidate will have a really good curve fit and detection over a relatively longer period of time. Less uncertainty around the peak temperature with a constant or a slow evolution in the color and the temperature. So this is the individual color band fit that you can see. This on the upper half of the middle graph, this is the combined color band. This gives an idea about the color evolution of the candidate that we have. This is the temperature evolution that is across the period of detection. It's also spit out the observed temperature. And this is the temperature evolution and a counterplot that shows us uncertainty around the peak temperature. What you have in here, I just put it so that you can find more information about it. This is the source ID for this candidate. This is the Babamul website that you can track more information about. And like I said, this is the peak observed temperature. We need to correct it for the redshift that we observe. So this is the corrected rest frame temperature, and that is the absolute magnitude for the brightness. So this is the lower limit on the redshift. This is the temperature and the absolute brightness calculated using that value. Sorry, I'm getting confused. Yeah, this is more difficult than doing all this. Okay, what are the limitations or the future work in our summer research project? As you can see that you need human vetting, or you have to analyze it visually whether the curve fit is good enough or not. So human vetting is needed to identify the most promising candidate. Threshold tuning for the Rubin scale data, because all the threshold that we used were mainly derived from other current sky surveys. So we need, as the sources that the Rubin detects, there will be some changes. So we need to tune those thresholds. So automation for processing millions of daily Rubin detection, and apply machine learning model to detect TDE. So takeaways, we identified 17 promising TDE candidates showing a potential of photometric classification for the efficient TDE discovery at Rubin scale. Sorry. Okay, acknowledgement. I'd like to thank my mentor. Robert and Julian, especially Robert, because he was like, really passionate with me as he told me about me earlier that I'm not in a typical astrophysical with a typical astrophysical background, but he was like really patient and yeah, he's just awesome. And of course, the GRAD-MAP team that provided me with this opportunity to research on this cool stuff. I went to Green Bank Observatory, and I will say I was looking at the heart of the Milky Way galaxy using telescope, and it was like poetic to me, and it was so precious. And of course, my teammates in this program, they were like really awesome. It was like as an observant, it was a fun experience, a learning experience with them. So yeah, huge shout out to them. So this is a summary of what we did or what we learned in our summit project. So I learned about TDE, what happens when an unlucky star gets too close to that black hole, a chance to study inactive black holes. And yeah, of course, the Rubin detect too many. I won't complain about that, to be honest. We built some multi-stage filtering and pipeline to reduce our like 10,000 sources to 17 promising candidate. The conclusion is that it shows the feasibility of Rubin scale photometric selections. So the future work, of course, you need to analyze it visually, threshold optimization for Rubin and automation for millions of daily Rubin detection. So that was for me this summer. I'd like to open the floor for the audience if they have any questions about my awesome research.
First you did amazing. I loved it. You had the slide 6, I believe. 6.
Okay, now I'm getting
Yeah.
Okay.
Yeah. Yes. So you had, like you said, 10,600 sources, and the 3,000, the 2,000, the 900 is all that was filtered out of that 10,000, right?
Yes.
And the 600 as well was the thing that was also filtered out of that. So how did you get 17? Because I'm adding up the numbers and it don't equal up to 10,000. So I was so like, and the what happened to the other sources? It's like if you know.
Okay, so I'll go back to this. So 17 candidates were from this thing, right? So, okay, I don't know how you add up, but this is like, in this, or what we did is that we have these sources, right? We apply this filter. So there were some of the sources that do not have enough data.
Oh.
So we will also took those sources out.
Okay.
So it's a good question, but I don't know if like this, that's how we did it. But yeah, so, but they do. I can show you more information about that thing. So I don't know if they add up and why don't they get around like 10,643? They should do, but yeah, I'll have more information on that. I'll get back to it. Yeah. Okay, so yeah.
Okay, so I think one big problem people are working out with Rubin is that I only have photometry, so estimating redshift can be hard. And I saw that you mentioned you use Photometric redshift. So when you do the selection, do you account for the uncertainty in the redshift when you shift the temperature to the rest frame?
Can you repeat that question again?
So like when you shift the temperature from the observed temperature to the rest frame temperature, would you consider the uncertainty in the redshift?
Yes, so that is the next part. So that's something that I observe in my, so okay. Sorry. Okay. This is a really so you see that there is a huge difference in between the redshift, lower limit of the redshift, right? So ideally, we want to have something that has a relatively less uncertainty around the redshift, so that the detection we see is like, okay, this is good because the redshift is consistent among all the detection that we have for the single source. So yeah, that's something that we also need to like look forward to, like when we do like machine learning stuff or something like that, yeah, that can be really handy. So that is the next step in our project, I'll say.
Thank you.
So we're gonna take a short 5-minute break at this stage, and then we'll continue with the second half of our office. So go to the restroom, get some coffee, food out there, and we'll be back in at around 11:05.
Metric, so yeah, it can be that large.
Well, that's like it's like a factor of 100 or something.
It's 2 plus or minus 1.5.
Insane.
Yeah, but that's because I like it's very uncertain what you're trying to do if you don't have a spectrum. You're just trying to analyze.
I feel like that sounds like a 20% error, but it's like
I mean, if you look at the temperatures and you factor in 2,
it's true.
it's actually not.
So, the host offset, is that from the center of the galaxy?
Sure.
Thank you.
Bring back.
How is it getting
Like
Like
I emphasize the side that are other black holes that are not just at the center of the galaxy.
So, I was just found one last week, yes, that is true, but most of like 99% of them are in the middle, so the assumption with the AGN is.
So it's basically saying that almost all of them are in the
99% in the middle.
That makes sense. You're not driving.
after this? Snacks? You guys are doing anything? Some
Like the person you. I just don't like to talk that. That's fine. I have other things to do. It's fine. We need this.
What's up?
Well, you don't like it?
It's really specific name, and we move more local. So it's like you can use the
Yeah, probably Taylor.
Taylor's a good name, but like when you have Saint John as your last name, that's just so cool. You have to. I mean, we can just call you Taylor St. John every time.
Let's just call you Gene.
Yeah, I like Santos better.
No,
I'm just Saint.
you know, very change.
It'll
It'll take some getting used to.
I know, right?
Start feeling the air.
I know, like I was like,
more.
low hair filter.
Yeah.
But I'm thinking though, like instead of him,
I started talking.
so I can like if I want to I have hair.
It's not an actual plan. It's always a way.
And I wanted to back to crazy. I wanna
I want to get one of
Kinda
these
crazy.
yeah, I wanna
Clipper Zero.
Yeah.
And
It's done, then we'll have.
How's that work?
I low key want
Always curious about that,
maybe
especially
buy
the air ones.
$50
Just stick forward.
just to buy you a
That seems like a
well, yeah, I want to make sure animation.
but basically, Sandro,
Okay, that's
JWST like
Give you like.
that's a lot of labor.
so basically what I'm thinking is we'll make
You have a lot of it.
a for people basically a Raspberry Pi but with
Yeah.
just because it's currently.
I don't work.
No, I even.
yes, but we're thinking about just making a cheaper so we can just
So that way to change over time.
it's already more expensive.
No veo mucho que
But also I can stop.
A dermatologist.
And we're thinking maybe aiming like less than $50, $30. But it doesn't have a peak.
Okay, I didn't think we were.
That's kind of it's a big jump.
Exactly, that's what basically what I'm doing. I just buy a just system on chip and then FPGA and then wire them.
That'd definitely be less than $5.
I'm looking forward to my here doing it.
Less than $50.
Let's come in maybe. I don't know.
It's just to stop around this. No.
Then also, I wanna like.
That's what you're gonna do? You gonna get a haircut? No, you're No, just for a little bit.
¿El baño dónde está? So you're same year in grad, but like not.
1 year apart in undergrad.
Oh, then they picked the wrong one. As well, so they're 3 years behind.
Well,
Graduate.
never.
It just takes longer, right?
You got this, I'm graduating in January 2029.
Yeah, no, we're gonna get along.
It's like, oh.
We haven't worked in like 4 days.
Yeah.
In the power outage now, so it's like,
Oh, yeah, apparently
each other.
they can kind of decide which buildings go out. No, I don't believe that.
Oh, really? No, my sister, but you have a set they're doing this, so they're adding like more like problems to you, so it's harder to you to work.
Right, it's okay.
Well, how?
It's fine. Wait, is the cluster?
Will have to. No, I mean like your job can be. I mean like it's
I felt as somewhat functional.
No, but this is Oh, it's Atlantic, where I'm fine.
This whole building, they do not affected. It's been created in collision.
What about you know if
Let's see. I think we're gonna do the last.
maybe believe that's the deal.
I'm sitting near the front.
I would honestly just act like everything's gonna go down.
Their whole campus is.
And they're also.
Might be blocking them
Yeah. They said they identified the issues, so hopefully they fix it for like.
Well, Doors been going down every day. Thank you very much. The NetBand says it's not our problem.
Go.
I think you already know that.
Nice.
We'll talk to like drag you in.
Just take the trains.
We're just taking van. The ski mask overhead. I go to the. I think the. Yeah, it is. No.
Nothing. I'm concerned about what's brewing and coming back.
Okay, we're gonna get started with our second half of presentations. Thank you all for joining us once again. So I'm Yash, I'm right there, one of Jackie's members. So I will say my own nice words about Jackie. And this doesn't even begin to like justify all the things I could say, but it has to be short. So Jackie is the first student that I've ever mentored for research. And because of her, I now have this unrealistic expectation that it's gonna be like really easy. Students. So she has this genuine curiosity in her, and that curiosity is the reason that despite at the start of the summer, we said, you know, we're gonna stay on track, keep our meetings to 1 hour. I don't think we did that successfully once. And I'm not complaining, because I've learned a lot as a scientist because of that as well. So I could not be prouder of what we've accomplished together with Leah and Chris in these last 9 weeks. And we're looking forward to working with her to continue this. So with that, it's beautiful.
Thank you. Hello, everyone. I'm Jacqueline Johnson, a physics major at Notre, Maryland University. And over the last 9 weeks, I've been working on modeling the X-ray reflection of black hole accretion disks. To start, here's the general structure of a black hole. This is the black hole. This swirling ring of hot particles is falling into the black hole, and it is known as an accretion disk. This blue aura up here is a powerful jet that expels high energy particles outwards and is powered by the accretion disk and the black hole. The picture I showed here is a little bit complicated, so we take important components of the black hole to turn it into a simplified model. At the base of the jet is what we call, the corona. The corona. And it is a source of high energy light, in other words, X-rays. Many models treat this corona as a single point source that is emitting in all directions. We can see some of the corona light, but many of these light rays also hit the disk, which is reflected back to us. In reality, we can't see exactly where the rays originate on the accretion disk system. Since we can't see the full picture directly, to understand what's going on around a black hole, we instead consider the reflected X-rays, which are only a small portion of the total light. To give an analogy, imagine a body of water that is as clear as a mirror. That is your accretion disk. Now imagine the sun as the corona. When sunlight shines onto water, it reflects off of the surface back into our eyes. And some of the light beams straight into the water and gets absorbed. The reflected light that goes back to our eyes can tell us properties of the water, such as its cleanliness or its movement. Similarly, light reflecting off of an accretion disk can tell us about the disk. The corona is constantly emitting many X-rays of high, medium, and low energy. Just like with water, some rays hit the disk and reflect, and by some fun interactions, which I'll discuss later, they reflect back to our telescopes. And also, some rays are absorbed straight into the disk. The collection of these reflected X-rays create what's known as the X-ray reflection spectrum. This raw data is gathered from telescopes and can be fitted into a reflection model. The model can then predict parameters such as black hole spin, inclination, and ionization, among many other parameters. Here is a predicted spectrum I created using the reflection model RELZIL. Along the x-axis is the energy of the X-ray photons. It's in log scale, so each tick is a factor of 10. Along the y-axis shows the energy flux, which is the amount of energy we receive at each photon energy per area per time. It is also on log scale. It's an arbitrary unit as we are prioritizing the physical shape of the spectrum and not necessarily its scale. The arrows represent different wavelengths of light from the corona. Each wavelength interacts differently with the disk. For example, the high energy X-rays shown here in blue, Compton scatter off of electrons to form what is known as a Compton hump here. Medium X-rays interact with iron in the disk to form this famous iron K emission line here. Low energy X-rays interact with other elements to produce other absorption and emission lines. You may be wondering, how is the reflection spectrum affected by properties of the accretion disk? There are many factors that affect the spectrum's appearance, such as the disk density, NE, or how much light is coming from the corona, which is the flux, Fx. If the disk is more dense, it increases the chances of the disk absorbing more light, which and less light would reach our telescopes. It also may cause more light to scatter in different directions within the disk, among many other interactions. The photons hitting the disk can cause ionization to occur through absorption. Ionization, Z, measures how strongly ionized the gas is, and ions relate to how many electrons an atom has lost. Ionization becomes important as it directly relates to disk density. If we were to keep the corona flux constant, then the more dense our disk is, the less ionization will occur. And vice versa. Those two variables are inversely related. And more intuitively, let's say a constant number of photons are hitting this part of the disk. If we increase our disk density, the same number of photons will hit a disk that contains more atoms, and meaning there's not enough photons to ionize all the atoms. Reflection models often have to make assumptions about how ionization behaves across the disk. Otherwise, computing the reflection spectrum becomes intractable. Here are two typical approaches. First, you have the constant ionization model in blue, where the disk is assumed to have one ionization value across the entire disk. Second, you have the ionization gradient model, where ionization is highest at the inner disk radius and decreases as you move away from the black hole and reach the outer edge of the disk. The equation on the right describes the gradient, but also if you set the power law alpha z equal to 0, you get your constant ionization model. So alpha z is the slope of the line. Let's see what changing ionization actually does to the spectrum. For constant ionization, as you increase the value of the ionization level, the spectrum begins to lose its prominent features. The yellow curve is low ionization at log Z equals 1, and there are deep absorption drops below 1 keV and sharp emission lines throughout the spectrum. Because the gas has plenty of neutral atoms. As we increase ionization with the red and blue lines, those features flatten out. With a log Z of 4, the spectrum is nearly smooth. A highly ionized gas has few neutral atoms left, so there's less absorption and emission, and the X-rays scatter more. For the ionization gradient, each panel depicts a different starting ionization value at the inner disk radius with log Z of 1, 3, and 4. The 3 lines in each panel are different slope rates, alpha Z. In the right panel, with log Z of 4 and alpha Z of 0, the entire disk is highly ionized, so the spectrum is nearly featureless, just like the constant ionization slide I just showed. Increasing the alpha Z index, as depicted by the red and blue lines, displays sharper spectral features. Higher alphas mean ionization decreases faster as you move outward from the black hole, allowing for more absorption and emission lines, emission of photons, which produces these sharper features here. In the left panel, where the starting ionization is already low, there's less changes to the spectrum when increasing the alpha Z index, as the whole disk is already fairly neutral. The extreme changes between a constant model and the more realistic gradient model reveals the importance of accurately modeling ionization across the disk. Yet, there's still a crucial piece missing. Each model assumes ionization to be a smooth function of radius. However, a real disk is turbulent. Based on general relativistic magnetohydrodynamic simulations, a real disk has random fluctuations in its temperature, and temperature relates to density. And remember, ionization is also related to density. Motivated by GRMHD, our goal is to create a model that can account for such random fluctuations. Currently, I've created an ionization profile within RELZIL using C++, the C++ language. The profile has a fluctuation centered at a chosen radius, and the formula shown here is the ionization gradient plus the Gaussian function, which creates one hump of a chosen amplitude. Here are ratio plots that I have created to compare our ionization profile with a smooth ionization slope. The amplitude is 1/10 of the starting Z value. And the spread of the fluctuation is 2 standard deviations, and it is centered at a radius of 10 RG. We are still working on the interpretation of these results. To further this project, we must first interpret the results of our single fluctuation profile. Then we can eventually add more fluctuations like shown here. These new models raise major questions. First, how large must the fluctuations be to have an observable impact on the spectrum? And second, how may these fluctuations affect black hole spin measurements? I'd like to thank my mentors Yash, Leah, and Chris, as well as GRAD-MAP, the Maryland Space Grant, and my home institution for this opportunity. Thank you. Are there any questions?
So, as the ionization is increases, we see a flat line, right? What is the actual cause of it?
As the ionization decreases
or increases? Can you go to the slide?
It's the
like before.
Oh.
Yeah, before. There's still, I think. Yeah, that's so. I think we can see like I don't know what was the variable, but like number 4, you have a flat line, right?
Yes.
And for lower amount of lower number of ionization, I don't know, value of ionization, you see some fluctuation. So what causes that difference?
Sure. So, like I said, ions relate to how many electrons an atom has lost. When you get sharp features like this, it's because either an atom has lost an electron and it shoots off an X-ray, which is what you see here. Like it's sending an X-ray back because it's lost an electron, and that is what gives us like a sharp line here. Yeah. And when you're highly ionized, there's less ionization happening. So there's less X-rays coming back towards our telescopes because it's already ionized. So there's no atoms to be lost or gained, or electrons to be lost or gained to produce these sharp lines.
Okay, makes sense. Thank you.
So I actually have 2 questions. But I'll just ask you one. But I guess my big question would be that if you're seeing, how would you be able to separate the disk reflection from the main coronal emission?
Great question. I actually need to talk to my mentors more about this.
Do you want the other question instead?
Yeah, let's.
I was just gonna ask, what's the dip? What's that steep dip at like 1?
Honestly, I'm not entirely sure about which features are what. There's other elements happening here that might cause deeper dips. The one I know the most is the iron line. It's like the most important one, which helps measure black hole spin. So I'm sorry, I can't answer this one.
I should have asked you better questions. I'm sorry.
It's a very good talk.
If it's gonna take like 30 seconds, then yeah, go for it.
Could you please explain that comparison to light reflecting onto the water and the telescope reflection?
This one. Yeah. So the accretion disk is a very reflective surface, kind of like a mirror. A mirror is very reflective. I know it's weird when you're thinking of particles. They can be reflective depending on the properties of the gas. In a similar way, gas is like a fluid of some sort, water is a fluid, and fluids can be reflective depending on the properties. When you see light hitting the surface of water, you can see it shining back into your eyes. Like, have you seen the sun blind you through the water before? That's kind of what's happening with the accretion disk. It's like a fluid, it's plasma, it moves like a fluid, and it hits some particles and they shine back to us and can blind you just like the water can. Yeah.
Awesome. Let's thank our speaker again.
Hey. Oh, yeah, sorry.
It's okay. Okay, right. Sorry. Next up is Anna, who is Anna Fernandez-Napp, which is from Prince George's Community College. And I have some words that her mentor, Dean, wrote about his time and working with him. He says, "It has been a pleasure working with her over the course of this project. Starting her first research experience in theoretical astrophysics is probably one of the steepest learning curves a student can ever face. Yet she's handled that challenge remarkably well. I have been especially impressed by her creativity in approaching research problems. Her genuine curiosity to explore every detail rather than simply accepting answers at face values, and her remarkable ability to learn challenging new concepts in a short amount of time. These qualities have made her a thoughtful and dedicated researcher, and I'm excited for her to share what she's accomplished with you today."
Down, yes.
All right, so thank you, everybody. My name is Ana Fernandez. I'm a recent Prince George's Community College grad in engineering. This summer, I worked under Ding and Massimo Ricotti on the Stellar Dynamics project, tracing the evolution of globular clusters with n-body simulations. So what is a globular cluster? And why do we care? So globular clusters are a unique stellar system, which are characterized by a few key features, mainly that they are nearly spherical and have high density cores. They are gas-free and they are located around the edges of our galaxy, so isolated. Most of the stars in these very large, very massive systems are coeval and low metallicity, but most importantly, they are very gravitationally stable and they are extremely old, with many of these globular clusters having formed 8 to 13 billion years old, almost as old as the universe itself, which means understanding their formation have very strong implications for the field of cosmology. Namely, if we understand their formation, this can reveal information about star formation at the beginning of the universe. These are some artistic representations, but also tangentially, the globular clusters can help explain the existence of supermassive black holes under the theory of cluster collapse. So we would love to just be able to observe all the way into the beginning of the universe and watch this process happen. However, that is not possible. And so instead, we have to use models based on our current physical understanding of these processes and simulate them in computers to test or to understand these complex systems, which is exactly what we did. So the first assumption of our model of globular cluster formation is based on current day observable star formation, which is that stars form from collapsing gas clouds, and that this collapse creates higher density pockets that are in a hierarchical and self-similar pattern, aka a cluster of clusters. And as such, stars form in this cluster of clusters pattern, and we theorize that they will merge from these multiple clusters into a singular large cluster, globular cluster. The second assumption that we make in our model is that we approximate globular clusters to be perfect Plummer density profiles. A Plummer model is this density distribution that is described by this equation, wherein the spherical density distribution described by this equation, wherein any point R in this density distribution is explained by the relation of the total mass of the system and the radius of the core. And this relates to what we observe globular clusters to look like today, with a very dense core and a diffuse envelope. And if we plot this density distribution on a log-log scale, we can see a flat core and then a power law profile out toward the envelope. The third assumption is that gravity is the main interparticle force driving the cluster formation from the initial condition. Basically, the pairwise gravitational forces between the stars drive the evolution and energy exchange of the system, and other mechanisms such as hydrodynamical forces from gas or stellar evolution operate on much larger timescales. And so for the timescales of our simulation, their effects can be negligible. And this is important because this means that we can simplify our very complex globular cluster to an n-body problem and use n-body simulations, wherein each star is simplified to be a single particle. So from now on, if I say particle, imagine a star in the system, and only their gravitational forces are calculated. So our methodology. So we decided to create a spread of n-body simulations from this cluster of clusters initial condition that we are trying to test, and investigate how parameters of this initial condition influence the final cluster formation. The main form that this simulation will take is that the initial condition is a plummer of plumbers. So it is a cluster of smaller clusters. The large cluster has a Plummer model distribution, and each subcluster also has a Plummer model distribution. Each subcluster is uniform with a total mass of 500 solar masses, which equates to about 1,000 particles per subcluster. we varied two parameters in the initial condition, R, which is the half mass radius of the cluster of clusters, the radius that encloses half the mass of the system, and the number of clusters in the initial condition, which is basically varying the total mass of the system. These R values range from the half mass radiuses of the initial condition range from 5 parsec to 40 parsec in a 4-step log scaled range. So we had, 5 parsec, 10 parsec, 20 parsec, 40 parsec. The number of subclusters range from 5 to 50, also in a 4-step log scale range, which means that we had from a total of 2,500 solar mass system to a 25,000 solar mass system. This creates, with these two ranges of parameters, we create a spread of 16 simulations varying these two parameters. And all of these simulations run for 500 million years for 1 million year time steps, or AKA the simulation runs for 500 time steps. And so this is sort of the same flow of these methods, but explaining how it works with our code. So we use two main coding packages, mCluster and nbody, and PTAR and nbody code. mCluster is a package that creates a Plummer model distribution. So we use mCluster to create our initial condition with the R and N parameters. And then we fill each particle in that initial condition with an identical Plummer distribution also created with mCluster. And then with all those 16 initial conditions, these run through PTAR for the 500 million years. And this is what our simulation can look like. These are two projections of all the particles in a 20 parsec and 23 subcluster initial condition. It's pretty cool to look at. And this is our entire spread of all our simulations in their final time step with their XY projections. Moving from left to right, we see larger initial half mass radius, and moving downward, we see larger total mass or larger initial number of clusters. The main thing we can see is that all simulations produce, or almost all produce, a singular central dominant cluster, which is promising with our hypothesis of producing a globular cluster. But just because we can see a central cluster does not mean that it is equivalent to a globular cluster. So we may see something like this and say, oh, that looks pretty much like, pretty similar to our Plummer model with a dense core and a diffuse envelope. Is this a globular cluster? Well, these are projections that can hide more information. This is a 3D space that the cluster takes up, and this projection can hide unresolved or unrelaxed substructures within the cluster. So when we plot a smooth density distribution over this projection and mark the relative maximums of density, we can see obviously there is a central cluster with a maximum density there in the center, but we can also see that there's some hidden unresolved or unrelaxed substructures, where there are higher peaks of density outside that central cluster. And so with this filter, we ran this over all of our simulations to select the ones that have more promising globular cluster profiles. So after doing that, we came to 6 cases that passed this filter. But this is not the only way to test if a cluster is a globular cluster. For systems that, like ours, where they are dominated by a conservative force like gravity, we can use energy to decide if the system is stable, particularly under the virial theorem. The total, 2 times the total time average kinetic energy of all the particles in the system should be equal to the total time average potential energy of all the particles in the system if the system is stable. That means that if we plot the total potential energy over the total kinetic energy of the system, the ratio should approach -2. And if we see the system, and if we plot this virial ratio over time, we should see the average approaching 2 if the system is stabilizing or virializing the way globular clusters. So from our 6 cases, we plotted their virial ratio over the entire time of the simulation. As you can see, there's a lot of fluctuations as the clusters are merging. But we also plot the horizontal dashed lines, which are their average virial ratio over time. And we see that several cases do approach this -2 value. And we can say that these systems are in quasi-equilibrium or reaching equilibrium, which means we can analyze them as globular clusters. So from there, we choose our 3 cases, which the best cases were the initial 10 parsec radius, half-mass radius with 23 initial clusters, the initial 10 parsec radius with 50 initial clusters, and the initial 20 parsec half-mass radius with 50 initial clusters. And we can plot their densities and their final snapshot of the simulation and compare how their density profiles compared to our idealized globular cluster model or the Plummer model. And so we can see that our filters worked and our density profiles are, approaching this power law that we would like to see, especially the 10 parsec and 23 initial cluster case. We can see a pretty relative flat core and then this power law distribution in the envelope, which is very promising for the initial condition being able to produce a globular cluster. So conclusions, like we said, almost all of the simulations produce central dominant clusters, and after filtering for energy and density, virialization and density, we found that those cases do exhibit the same properties as globular clusters. And also qualitatively, we can see that there is a trend between larger initial condition, half-mass radii, and the final half-mass radii of the resulting cluster. Of course, these are sort of qualitative trends, and so we would need to run many more simulations to really corroborate these results, but they're very promising initial results. So for the future work would include running many more simulations and statistical analyses of these simulations. And that is all. I'd like to thank my mentor, Kai Ding, and Massimo Ricotti for guiding me this summer, especially through all my frustrations with my very first research experience ever, with my very first dive into astronomy period, and also all of the GRAD-MAP leads, Mark, Yash, Marshall, and Lynx for being incredibly supportive, not just helping me with difficult astronomical concepts or physical concepts, but also just emotionally being there for me throughout the harder parts of the program. And then, of course, to the lovely astronomy department and all of my peers in the program for just creating an incredibly welcoming environment. So thank you.
Maybe we have time for maybe a couple quick questions.
I have a really quick question this time. It was a great talk. You did jump scare me with the virial theorem. How computationally intensive are these simulations?
What do you mean by that?
Just so my assumption is that if you're doing n-body simulations, it's just taking a lot of computing power.
Yes.
And my question was, do you have a rough idea of the scale of them? How long does it take to run one of these?
So the uniqueness about PTAR is that it can use multiple cores and also GPUs, so it can be more efficient in that way, but it definitely takes a lot of computing power, and some of the larger simulations can take around a day.
One more.
Can I see your summary slide again? I wanted to see what you said.
Sorry,
The first item in the summary slide said almost all simulations, and I would be worried Was that the summary slide?
Yeah, sorry. I was gonna go back to
Yeah, almost all simulations produced a dominant cluster after 500 megayears. The ones that didn't, why didn't they do that? Did you stop at 500? Would they have formed one cluster if you went to a gigayear, or is there something else going on, like an escaper?
We believe that they would viralize if the simulations ran longer. Also, of course, there is some randomness in each of the initial conditions that we create for the simulations. So it's not necessarily a result of the initial condition parameters that certain cases didn't produce a single dominant cluster. If we repeated these simulations with the same parameters for more iterations, we would be able to tell for sure what leads to the pattern of not having a single dominant cluster. But yeah, I'm not sure exactly what.
Okay, so last but not least, we have Tuan. So his mentor Yeji wrote, it was a pleasure working with you this summer, Tuan. I was especially impressed by the way you consistently took the initiative to work through challenging problems on your own rather than relying on my guidance or AI tools. Since this was likely your first experience working with astronomical data sets, you approached the project with curiosity and a willingness to learn. I hope this experience opens the door to many exciting opportunities in your future academic journey. Congratulations on all your hard work, and I wish you the very best. So we'll hear from Tuan now. And before he gets started, after this presentation, we'd love for you all to hang around for a few minutes. We'll be doing a few certificate presentations to all our scholars for a few minutes after. Yeah, go ahead.
Good morning, everyone. How are we doing? Do people in the back hear me clearly? Yes, thank you. So I'm Tuan. I'm from Dickinson College, and this summer I worked on a project developing a AI model to detect comet, a Nielsen comet in stereo image. From this title, you probably wonder what are Nielsen comet and what is stereo image, and what AI model did we use? It could be ChatGPT or Claude or whatever. but it's my outline presentation. We will talk about what are stereo, comet, and CNN, and how did we build our CNN and our result at the end. So stereo, or you can call it as stereo, is a solar terrestrial relation observatory, which is a space telescope. There are two spacecraft launched by NASA in 2006, and it observed the sun, and it collect like million image of solar image. So there will be some Nielsen comet appear in those image. And the next stuff we talk about is comet. What is comet? It is a small icy body, consists of dust, gas, and ice. So normally it's a rock, but when it's near to the sun, the heat and solar flare will evaporate the icy gas, and which produce dust cell and gas cell of the comet. So here is a comet image in stereo image. And the next step we talk about what is CNN, which is our AI model. Inspiration of neural net, CNN, which stands for convolutional neural network. And what is neural network? The inspiration of it is based on our biological neuron, which has these tentacle to like get input in, and then it's gonna process that input and transit them into here, which is our output. And artificial neural network based on that idea, they take input and they calculation, and then they transit via those arrow, and they will have the output at the end. And convolutional neural network is the model that like our human when we see like thousands of image, like we see face, we will recognize the face by pattern, and CNN also based on that. For example, if I give CNN like 1,000 image of comet, they will try to remember and extract the feature from those image and study that. For example, if I give and I'm sorry. As I mentioned, these new sun comets have a long tail like this. That's a feature that CNN will looking for in our image. If I give the image like this into CNN, they will see that, oh, there's a bright stuff in the middle, and there will a long tail, quite long tail behind it. And with this is the CNN, they will remember that feature. So, example, if I put this image in, they cannot recognize a comet because like there's no tail or like bright sources. No, it have bright sources, but it had no tail, so they will classify as which is not comet. And how did we build our CNN? So to have a smart CNN, we like a human, we need to study to be smart. So CNN has need like we need both. CNN need a training data set to like thousands of images to remember them. Then CNN will learn it, and then like human we study, and then we take exam to know if we study correctly. CNN also have a test like that. We have it's called model evaluation. How did we train our training set? We use image from CATCH, a Comets asteroid telescopic catalog of. It's a tool from small body group in UMD. So this is a sample of image from CATCH. This is a whole image. Then we crop them a size of 100 x 100 pixel and fit them into CNN. But before fitting those images to CNN, next up, we need to label them. So this is CVET label interface. We use CVET, which is a tool to label images. So we label them at like 0 represent comet and 1 is not comet. After we have the training data set, so we have 9,000 labeled image. We go in our CNN. So our CNN had like feature like we have optimization to reduce model error, and then we have scheduler to improve the learning rate. And we train we run 30 epoch, which is like 1 epoch equal to 1 time that our CNN see every image in our training data set. And after 30 epoch, we've take the best image that we have, and this is our result. So the best model loss we have is 0.9, which is quite, I believe, is good. Loss here means that the difference between the model prediction and our label. So like the model error, you can understand that way. And our accuracy was 90.7 and 97%, which was good to some people, but I don't believe in this number. Because like this is a sample that we take out from prediction. So you probably see this one quite comet feature quite appearable. This as well. But for example, this one they label as comet, but it's quite not clear to see the tail. You can see some tail like this, but it's not, I believe so. And for example, they label this as comet as well, but you don't see the tail. This have the tail, but yeah, is not really clear like this as well. So I don't believe in this accuracy. So the next step we're gonna do like future work, we will try to first off we will try to improve our model first, because like 9,000 image is not a big training set enough. So we will try with bigger training set, and then we would test with like full resolution zero image, and we would try to detect some like unidentified news and comment at the end. So I think that is it. Thank you for. Yeah. Go Dion.
So you said earlier that your and your results were kind of bad. So is there a way, because I know you said earlier too that y'all basically like y'all zoomed in on the images, like not say screenshot it and like you zoomed in on the images to like get to like have the accuracy, but is there any way that y'all could have obtained, I guess, the picture of just the comet itself, or it had to be with the other materials or stuff inside of those other pictures to improve the accuracy of it? So I think so. Can you resume to like your slide of like where like it showed the images, like the one beside that? Yeah, this one. Yeah, that one. So like, and you see how how like the system said that all of those are comets. Is there any way to filter out anything that is not said comet, or it has to show all of those things in the images?
I don't get the question. I don't get the question.
Is there a way to filter out anything that is not a comet
at the end, like after our prediction?
Yeah.
So in fact, I don't think we have way. Instead, we need to improve the model to better prediction.
So have you ever tried to maybe rotate a picture, like rotate images? Because technically there is a comet, it doesn't depend on rotation or the orientation. So if you just like rotate the picture a random direction, they can like double your training set without like adding any new data point. And by fitting that into the neural network, they're gonna scan for the same pattern again, but it will like be more robust in a way that like adds more data points without adding like new like images. Would that be a possible thing to do in this framework?
So in fact, we have to think about that, but we realized that rotating those images quite like we did everything programmingly, so we didn't have like, for example, when we get image from catch, like those images are really random, so we just like crop out this, and like they can be in any direction, so we don't choose to rotate them because it's not a way to rotate them like in one direction. Like they are multiple one, but if you want to choose like you want to rotating them like this a direction, it's hard because like I don't think there's a strict way to do that, like a way to do it.
We're probably going to save questions till lunchtime. So if you have more questions, you can ask our scholars. Tuan again. Okay, so we'll be calling our scholars up.
Oh.
This was us at Green Bank a few weeks ago. Yeah, we had a really good time up there for a few days, so. Yeah, we'll miss you. This is the time where things are most active in the department in the summer, so. Thanks for making it a lively place and bringing all of these people together for a big event, which is rare in these months, so. Yes.
And so first, we're going to be giving certificates to all our summer scholars. So first, we're going to have Dion step up and present your certificate. And, oh, wait, don't go yet, because we have secondary awards, which is your second one in here, which are personalized to you, where you have the Galactic Winds of Change Award for pushing through the challenges as they can. Journey may have been a struggle, but your determination got you through. You displayed a steady drive that pushed you through the turbulence.
Okay, next up, we have Diepanh.
It's not, oh, you revealed them.
Oh, wait.
Oh, did we not have the regular one in there?
Yeah.
Oh, it's fine,
They're fine. And you get the Melting the IceCube Award for proving that even the coldest challenges can be conquered with warmth, kindness, and determination.
Right. All right, next up we have Ashok. And your regular certificate, but your personalized one is the Transient Traveler. Receiving a lasting impression. Transient events may only last seconds, but their stories can last forever. The engagement, kindness, and drive you showed in this program will be remembered by all those that were lucky enough to work with you.
Hey, Jackie. Oh, I took the wrong one out for the picture.
Thank you.
Yeah. X-ray X Factor Award for bringing the zing to the recipe of AGN X-ray. Among the highest energy processes in the universe, your passion and drive shine just as bright. You're the X factor to X-ray spectra, organized, driven, and impossible to ignore.
Yeah. Anna, oh wait, who's this? Oh, was that your? Okay, sorry. Great, thanks. All right. And you have the Gravitational Gold Star Award for proving that the strongest forces in the universe are curiosity, diligence, and a good heart. You took ownership of every star cluster you simulated, always chasing the bigger question behind the numbers, all while putting in long hours to reach your building for yourself. Yeah. Oh, yes.
And your special award is Blazing a Trail Award for teaching a neural network to find comets and teaching all of us what quiet persistence looks like. You kept asking the right questions until the picture came into focus. Every hurdle you hit, you cleared it. Like the comets you searched for, you left a trail this summer that was hard to miss. Okay, so one more round of applause for all 6 of our summer scholars. We have sort of a first come, first serve lunch that will be outside. Should be all set up there. And thank you all for joining us. We had such a great time today.
Looking at it. I went, I did time. In July. July.
Out the.
Be like. I was gonna be big brain, LOA.
Can I get you want to slide?
He was like, my babies, I'll feed you.
Yeah, of course.
Yeah.
Can I? Can have one of these ones?
Tastes like fish food.
I don't believe it.
I kind of didn't. I was
Stay.
like at 9:12
Group should stay.
because I was on my alarm, and then I got here, and then I had to leave when I woke up, so I never for about.
Yeah, we're gonna go prepared.
And Shannon.
And Bennett, Shannon and Rich.
Oh, Shannon had to go.
Well.
Oh, there's Bennett.
Bennett, stay here.
Okay. Somebody else.
Good group picture. Was it?
Actually, because of.
An amazing job. I'm
Why would
sorry,
you
I
do
wasn't.
this?
No, I felt like.
But the thing that I love
With the slides or
about
like.
Robert too.
before
Yeah.
Yeah.
Neophytes, like